Okay, in this section, we're finally going to complete our family of tests on the convergence of series with the root and ratio tests. So before we get into those tests, we need just a little bit more vocabulary. Let's quickly define what those are. So given a series, we may consider an associated series with only positive terms. So basically, every term of this associated series is the absolute value of the original series' terms. Now, if a series only had positive terms, then this particular absolute version of the series is exactly the same thing. So really the context here is that this original series is maybe an alternating series, and this series here is kind of the unalternating version of it. It's the version where you don't have the negative alternating sign. So, okay, well, this series AN we would say is absolutely convergent if this series here is convergent. So let's quickly look at an example. Let's consider this series here. Okay, so this is clearly an alternating series. Yeah, but since the absolute value of this term is just 1 over n squared, and the series consisting of just that 1 over n squared is convergent, okay, let's quickly justify. It's a p series. P is 2. 2 is strictly greater than 1. Then we can conclude that the series under consideration, which was this alternating series, is absolutely convergent. So note that if a series is absolutely convergent, then that automatically would imply that the series is convergent. All right, so what if you have a series that's convergent, but not absolutely convergent? All right, well, this would be called a conditionally convergent series. All right, so just as a quick example of one of those, let's consider this particular series. So again, this is an alternating series, and we can show that by the alternating series test, this series is convergent. However, the absolute version of that series would simply be the series 1 over n. And we know that that series is divergent. Why? It's harmonic. So we would conclude that this series here is conditionally convergent. So to be clear, both conditionally convergent and absolutely convergent are convergent, right? So they are convergent as we understand that term. The adverb conditionally or absolutely, what they do is they give us information about the absolute version of the series. Okay, so again, in the last example, we had absolute convergence. And it doesn't mean absolutely like, hell yeah, this thing converges. Absolutely it does. I mean, sure, it can mean that. But the absolute there means that if you take the absolute value, if you throw away the negative ones, you still have a convergent series. So the reason that this series converges is more to do with the structure of it, the fact that these 1 over n squareds get small very quickly, and therefore this is an absolutely convergent series. For the conditional case, we say this is conditionally convergent, and that's because it's convergent, luckily, because it's an alternating series here. But if it were not an alternating series, the structure of this thing is not enough to converge on its own. That's why we make this distinction. So, all right, let's break this down. If you have a given series, So far, we understand it has two behaviors. The series can be divergent or convergent. But now we have two more classifications. If the series is convergent, it's either absolutely convergent, and that's if the series is convergent with the -1 removed, so in other words, the absolute value, or we can categorize it as conditionally convergent, and that's if taking out the -1, in other words, absolute value of the terms, would yield a divergent series. So that's basically what we're looking at. If a series only has positive terms and it's convergent, then it's automatically absolutely convergent. So again, these two categories we really only talk about if we're dealing with some sort of alternating series. Okay, so we're going to determine whether this particular series is absolutely convergent, conditionally convergent, or divergent. So, yeah, the thing is the approach to answering this question depends on making a very good educated guess about the answer. So, we're just going to think about this for a minute, and we're going to start by asking ourselves, what is the behavior of this series here, the absolute version of that series? And hopefully, at this stage in the game, you're looking at that and saying, yeah, this is going to be a convergent series. And that's because it's kind of like 1 over n cubed. And we can establish this behavior using the limit comparison test. So if this series is convergent, which it is, we know exactly how to prove it. That means that right away we can conclude that the original series is absolutely convergent. So notice we haven't written a single thing. I mean, this is actually a thought bubble that we didn't really write. We're thinking it. So we haven't written anything. Okay, so now we need to prove that this series is absolutely convergent. Well, the easiest way to do that is actually just to prove that this series is convergent, and then you're done. Okay, so we're going to simply show that the absolute version of this series is convergent. So how will we do that? Well, with the limit comparison test with this p-series. It's probably the easiest thing to do, right? Because this is purely algebraic. So purely algebraic means use the limit comparison test with the sort of obvious p-series that has the same relative degrees as what's here. So in this case, that'd be 1 over n cubed. Okay, so let's quickly carry out that limit comparison test. So of course, we write this as the terms that we're interested in multiplied by the reciprocal of the terms we're comparing to, and this limit here comes out to 1. So what is it about 1 from which we can draw our conclusion? It's not 0, it's not infinity, right? It's a positive number, strictly greater than 0, strictly less than infinity. And what is our conclusion? Is that these two series have the same behavior. Okay, what behavior is that? We haven't really established it yet. Well, 1 over n cubed is convergent. Why? It's a p-series. 3 is strictly greater than 1. Therefore, 1 over n cubed minus 5 is convergent. All right, so we have shown that the absolute version of this series is convergent, which means we can draw the conclusion, the main conclusion, which is that the original series we're interested in, which was this alternating version of it, is absolutely convergent. And there we are. Let me just point out that it would have been a waste of our time if we'd approached this by starting with the alternating series test. Certainly, using the alternating series test, we would have seen that this series is convergent, which would rule out the divergent case. But once we have this thing convergent, we still don't know whether it's absolutely convergent or conditionally convergent. And to answer that question, we would need to consult the absolute version of the series and determine whether that series was convergent or divergent. So we'd still have to do this work anyway. So if you're expecting absolute convergence, which we were, then all you need to do is show that that absolute version is convergent. And once we have the convergence of this series, we get to conclude that this series is absolutely convergent right away. Okay, so let's think about what the absolute version of this series looks like and what its behavior might be. So that particular series we can expect is divergent. And you can establish that by showing that these terms are actually greater than the terms of the harmonic series, which is divergent. So using direct comparison with the harmonic series, we can show that this series is divergent. So that rules out absolute convergence of this series. Now, does this original series converge or diverge? Well, if we apply the alternating series test, we are basically going to be taking the limit as 1 over ln of n as n goes to infinity. And this guy does approach 0. So we can expect that this series will converge by the alternating series test. So yeah, we probably are going to have that this is a conditionally convergent series. So to show that a series is conditionally convergent, there are 2 steps. You have to show that the series itself is convergent and that the absolute value version of the series is divergent. Okay, so let's do both of those things. So we'll start by showing that this series is divergent. And we will use the direct comparison test with the harmonic series. Direct comparison test we know is 3 steps. So the first step is establishing the comparison. So 1 over natural log of n is certainly greater than or equal to 1 over n. That's true. The next thing is establishing the behavior of the series you're comparing to. So this is a harmonic series, it's divergent. Let's just treat it as a p series this time. We could write p is equal to 1. What is it about 1? 1 is less than or equal to 1. All right, so our conclusion is that this series is divergent. Okay, excellent. So we've completed step 1. This rules out absolute convergence of the original series. All right, so the last thing to do is just to show that the original series itself is convergent. And we'll use the alternating series test for that. So we need to acknowledge that 1 over ln of n is decreasing. Okay, certainly true, because ln of n itself is increasing, and this is 1 over that. And the other thing is just quickly taking this limit, and I really do mean quickly because there's really no work to show. You get immediately the form 1 over infinity, which means the limit evaluates to 0. So we conclude okay. Okay, so one more example on this particular type of classification. And by the law of 3 examples, can probably expect this one to be divergent. But let's prove it. So indeed, just looking at this thing, we would expect it to be divergent. I mean, 2 to the stuff, that's going to grow. And then the alternating part just means it's going to be really big positive number, followed by even bigger negative number, followed by even bigger positive number, and so on. So yeah, when you have that kind of behavior, which isn't very common, you can use the divergence test. That's just a matter of evaluating the limit of the terms here. And what do we get? Well, does not exist. So that's not 0. Therefore, the series is divergent. Let me just remind you something about the test for divergence. I said it back when I was introducing this test, but that was so early in the game that that what I said may not have resonated at the time. So I'm going to repeat that. That was that the test for divergence can never be used to establish convergence of a series, right? It either is going to show you that the series is divergent because the limit approaches something other than 0, or the test is inconclusive, right? So we understand that the harmonic series is divergent. However, if you apply the test for divergence to it, you would get the limit equaling 0. So when you test for divergence on a series and you get that the limit equals 0, it's just inconclusive. You learn nothing. That means the series could converge, series could diverge, whatever. It's a very short test to carry out, but there are very few cases where it actually is useful. This is one of them. Okay, we are now going to see what is personally my favorite test out of all of them, and what I consider to be the most powerful out of all of them, which is the ratio test. So we know how geometric series kind of work. A geometric series has the form AR to the n. Well, n minus 1 if you wish, but doesn't matter. You can just offset. So AR to the n. And we know that if the absolute value of r is less than 1, then this series is convergent. Whereas if the absolute value is greater than or equal to 1, then this series is divergent. Okay, so we would really, really love to have an analogous test like this for any series, right? This only works for geometric series. What the ratio test does is it sort of shoehorns any given series that you're working with into a geometric series. And you kind of extract this sort of R value and you compare it to 1, and you draw a similar conclusion as to what you would have here with the geometric series. So how do we take any old series and shoehorn it into the universe of geometric series? Well, with a geometric series, we can just see this R value, right? We pull the R value right away by looking at the term of the series here. For any old non-geometric series, you don't have that R value, obviously. However, if you think about what this R really is, it's really any term of this series divided by its previous one, right? So, I mean, that would be, for example, the n plus 1th term divided by the nth term, and this actually gives you R, right? The A's cancel, and you're just left with R. So for a geometric series, you literally get R. But for any old non-geometric series, you could still take this ratio and get something that would sort of be equivalent to what your R would be, right? It wouldn't necessarily be exactly a constant. In fact, for a non-geometric series, it won't be. But we could take whatever that thing is and compare that to 1. And in fact, if we get something less than 1, we have a convergent series. And if we get something greater than 1, we have a divergent series. And that's the ratio test. That's all the ratio test is doing. And it's exceptionally powerful. So let's suppose we have a series that we're interested in, and we're going to let L equal the limit as n approaches infinity of the absolute value of an plus 1 over an. So basically, a term divided by its previous term. Okay, now you're going to get some sort of expression involving n, and then you take the limit as n goes to infinity, and you're actually going to get a literal number out of that, right? So now, what's our conclusion? Well, if L comes out to be less than 1, then the original series is absolutely convergent. Okay, so that alone is a very powerful conclusion. If L is greater than 1, then the series is divergent. And if L is equal to 1, now this is the one problem with the ratio test, then the ratio test is inconclusive. And it's for this one reason right here that unfortunately the ratio test can't be just our one-stop test for everything, right? It's our one-stop test for a lot of things, but not everything because of this stupid dumb L equals 1 case, which comes up an annoying number of times. So let's see how to use the ratio test. All right, so let's look at this one. Now, the ratio test really shines when you have a single term over a single term, and when the entire series is not algebraic. It's okay for part of it to be, like we have an n cubed here, but if the whole thing's algebraic, well, go to the limit comparison test. So let's see how we would use the ratio test here. Well, the ratio test has us calculating the following L value here, and its limit as n approaches infinity of an plus 1 over an within absolute values. So that would be the limit as n approaches infinity of an plus 1. Well, that's going to be everything, all the n's replaced with n plus 1, divided by an. And of course, let's multiply by the reciprocal of an. So that would be 3 to the n over n cubed. Okay, so we just have to work out this limit. Now, with the ratio test, everything's going to kind of have a friend. So like we've got this polynomial here. So let's line it up with its friend. And we have this exponential 3 to the n. Let's line it up with its friend. Because you're going to get some cancellation with some of these friendships. Like 3 to the n over 3 to the n plus 1, that's just 1/3. Also note, we don't even need the absolute values here because everything's positive. Okay, so we're ready to evaluate this limit. This part here just goes to 1. So this entire limit evaluates to 1/3. Okay, what is it about 1/3 from which we can draw our conclusion? Well, 1/3 is less than 1. So this series here is convergent. Now, in the wording of the ratio test, it did say absolute convergence, but that distinction isn't really necessary when you have a non-alternating series to begin with, right? But it wouldn't be wrong to say absolutely convergent. It's just redundant. Okay, so yeah, let's use our favorite new thing, which is the ratio test. This is perfect for it. It's a single term over a single term, and it's got factorials. And ratio test is really good with factorials, right? So from now on, if you see factorials, you should really try to find a way to use the ratio test. So yeah, let's do that. So we're going to let L be this limit here. Okay, so a sub n plus 1 is 2 raised to the n plus 1 squared. This is all over n plus 1 factorial, and then multiplied by the reciprocal of an. So again, we can throw away the absolute values, but let's take a moment and line everything up with its friend. Okay, and maybe there's some cancellations here. So let's quickly FOIL out this n plus 1 squared. We know that's n squared plus 2n plus 1. And if we divide 2 to the that thing by 2 to the n squared, we know the n squareds will cancel when you subtract the exponents. So this is going to be 2 to the 2n plus 1 multiplied by, what about here? We have a factorial battle, and we know that the denominator can be written as n plus 1 times n factorial. So the n factorials will cancel, giving us 1 over n plus 1. So we just have to work out this limit. Okay, well this is like 2 raised to the infinity. So that's going to run off to infinity, but we have infinity in the denominator as well. That's annoying. Okay, so to work out this particular limit, we're going to need L'Hopital's rule, because we get the form infinity over infinity, and there's no obvious algebraic way to handle this. So fine. To use L'Hopital's rule, though, we're going to need that auxiliary f of x function. And we'll just evaluate the limit as x approaches infinity of f of x. Oh, right. This, of course, goes to infinity over infinity. But now we have license to use L'Hopital's rule. So derivative of 2 to the stuff is 2 to the stuff times ln of 2 times the derivative of that stuff. So derivative of 2x plus 1 is just 2. And the derivative of the denominator is 1. Okay, so taking x to infinity, we have this factor, which approaches infinity, of course, very quickly, multiplied by, who cares, this limit is infinity at this point. Okay, so this means that L evaluated to infinity. And what is it about infinity from which we can draw our conclusion? Specifically, infinity is greater than 1, right? Last I checked. Therefore, this series is divergent. All right. Before we fall in love with the ratio test too much, I think it's important to see a situation where it completely falls on its face. And like I've said before, that would be when you have a purely algebraic series. So let's be clear. We already know how to handle this one, hopefully, because if you have something purely algebraic, that means go and use the limit comparison test. We would compare this to the series rad n over n cubed, clearing away all the clutter. And in fact, this guy would be 1 over n to the 2.5 after you subtract 1/2 from 3 to get this purely in the form of a p-series. This is a convergent p-series. Of course, 2.5 is greater than 1. So by the limit comparison test, you can tie the behavior of this series with this series and then conclude that this series is convergent. So great, we have a way of doing that. But what if you're just so in love with the ratio test that you want to use it all the time? Well, let's see what would happen if we did use the ratio test on this. Well, we would let L be this limit here. So n replaced by n plus 1. And then the reciprocal of the series would be n cubed minus 3 over rad n. So everything's positive, but line them all up with their friend. So we have radical n plus 1 over radical n multiplied by n cubed minus 3 over n plus 1 cubed minus 3. Okay, so now this is a purely algebraic limit, so we don't need to use L'Hopital's rule. We can just compare the degrees. This part here, the degree on the top and the bottom is 1/2. So this part goes to 1. And this part here, the degree on the top and the bottom are both 3. So that part goes to 1. And in fact, this limit will just evaluate to 1. And sadly, if you do the ratio test and you get L equals 1, it means you've just wasted your time. It doesn't mean it probably converges or diverges. It doesn't mean any of that. It means we don't know anything. We've learned nothing from this. So the L equals 1 case means the ratio test is inconclusive. So in the interest of saving you some grief and frustration, never use the ratio test on a purely algebraic series. You're always going to get L equals 1 if that happens. So yeah, of course, use the limit comparison test. We already have that case handled. All right. Here's another one where we have a factorial, and the factorial strongly suggests that we should try to find a way to use the ratio test. Now, the problem here is that we don't just have one term over one term. We have one term over two terms. And if you've got a plus or a minus in there, that's going to make the ratio test a little bit more difficult. Not impossible, but let's just sort of jump ahead and see what this particular form would look like. Because this is what we'd have to take the limit of, right? So an plus 1, that would be 1 over n plus 1 plus n plus 1 factorial. And then we're multiplying by the reciprocal, so that would be n plus n factorial over 1 here. So this would give us something like this. Now, we'd really like to get a bunch of cancellations to occur so that we can take this limit. But the problem is that we can't have the factorial battle worked out the way we want, because you can't cancel terms like this, right? You not when there's pluses. I mean, that's just algebraic nonsense. So yeah, let's avoid that situation. And in general, try to avoid using the ratio test when you have like a little plus or a minus down there. Okay, so what will our approach to this be? Well, what we're going to do is sort of use the comparison test to drop an unwanted term. So in particular, what I mean by this is we're going to show that 1 over n factorial as a series is convergent. And for that, we'll use the ratio test. So let's assume that we're able to do that, and we are. Then we're going to conclude that since the term of the series we're interested in is smaller than the term of the series we just showed using the ratio test is convergent, that the series we're interested in is convergent. So this is what we mean when we say we're using direct comparison test to drop an unwanted term. All right, so we kind of dropped that n from the original series. All right, so let's kind of do step 1 here. So an plus 1 would be 1 over n plus 1 factorial multiplied by the reciprocal of an. So we have n factorial over n plus 1 factorial. We don't need the absolute values, of course. And we have a little factorial battle here, which resolves to this. And that limit, of course, equals 0. 0 is less than 1. Therefore, this series here is convergent. All right, and for our comparison test, we need to quickly acknowledge this very obvious thing. And now we can conclude that the series we're interested in is convergent. Okay, so the root test is our very last test we're going to learn. And it pretty much does exactly the same thing the ratio test does, but it just grabs that number a different way. So whereas the ratio test extracts that mysterious r value from a series by comparing an plus 1 over an, what a root test does is it grabs that r value by taking the nth root of the nth term. And again, if we sort of look at the structure of a geometric series, then the nth term is ar to the n, right? But imagine that we took the nth root of the nth term. Then we would get the nth root of a times the nth root of r to the n, which is r. Okay? Now, if we took a limit to infinity, well, it doesn't matter what a is. As long as a is a constant, this guy here would kind of go to 1. And we would get that r out of that limit. So this is just another way of pulling that sort of r value out of an arbitrary series. So let's see. So suppose we have a series, and we're going to let L, instead of being the common ratio, we're going to now say L is the limit as n approaches infinity of the nth root of the nth term. And yeah, we can throw the absolute values in there. Another way of writing this is the nth term raised to the 1 over n, of course. The conclusions are going to be exactly the same for the root test as they are to the ratio test. So if L is less than 1, then the series is absolutely convergent. If L is greater than 1, then the series is divergent. And if L is equal to 1, then the root test is inconclusive. Before we go and do some examples, I would like to just write down a few useful limits that we can take for granted. The first one here we worked out in an earlier section. That is e to the s. Okay, you certainly need to know the proof of that, because this limit may come up a slightly varied form of it, in which case you're just going to have to go through that process of, with the natural logs and so on. But if you see it in exactly this form, boom, you can rewrite it as e to the s. So, and it does show up in that exact form quite a lot. Here's another one, useful fact. The limit of the nth root of n is equal to 1. And that's not a trivial limit. That may look like something silly, but it's not trivial. You'd also have to show that using logarithms and so on. But that limit comes up so much, we're just going to say that equals 1. And in fact, this is true for a constant down there, provided the constant is positive. Okay, so let's see some examples. Okay, so with this series, what is it that tells us we should probably use the root test, other than the fact that we just introduced the root test? Well, that is when you have a term that is a whole bunch of stuff raised to the n. So if it's just stuff raised to the n, then yeah, that's a really strong indication that you should use the root test. So
we'll do that. Right.
So it's the nth root of the absolute value of an. Okay, so the nth root of this stuff, which is already positive, raised to the n. Well, you can see why this is perfectly engineered for the root test, because the nth root of stuff to the n is just going to give you the stuff. So we're just left with this. Okay, yeah, well, that's a purely algebraic limit with degree 2 divided by degree 2, so it's just going to be the ratio of leading coefficients. So this evaluates simply to 1/3. Great. What is it about 1/3 from which we can draw a conclusion? Don't ever forget this part, right? 1/3 is less than 1. Therefore, this series, I don't want to write the whole thing, we'll just go like that, is convergent. And there we are. Isn't that wonderful? Okay, so here's another perfect candidate for the root test, because we have a bunch of stuff raised to the n. Well, you might be looking at this and saying, it's not raised to the n, it's raised to the n squared. Yeah, but stuff raised to the n squared is still stuff raised to the n, right? It's just that that stuff itself is something to the n. I'll worry about that later, though. So let's dig in and do the root test. So that's the nth root of this thing. So the nth root of the absolute value of 1 minus 1 over n to the n squared. All right, well, as n gets large, this quantity is always positive, so we don't need the absolute value. And taking the nth root of that thing means that it's like we're dividing the exponent by n. So you're going to see that this is just the limit as n approaches infinity of 1 minus 1 over n simply to the n. All right, now pause the video and work out this limit, although there's no work to show. But what does this equal? This guy as a form is like 1 plus negative 1 over n to the n. And if we take that limit as n approaches infinity, this is going to equal e to the negative 1. Okay, by that shortcut formula. So again, you have every right to use that shortcut formula when it applies, as it does here. We have e to the negative 1. What is it about e to the negative 1 from which we can draw a conclusion? Is it greater than or less than 1? Well, you just need to know that it's less than 1, right? E is about 2.7. So 1 over e is 1 over 2.7, which is, of course, less than 1. So that means that this lovely thing is convergent. Cool.